Okay, so I wanted to give at least some contextualization of what I do in my group, which, as Jason mentioned, I've been working on reinforcement learning for a very, very long time, since my thesis days, which before most of you were born. So I work on basic questions in reinforcement learning, abstraction, temporal structure, abstraction hierarchies, partial observability, all the kind of interesting topics of the foundations of reinforcement learning. But like most of you, when deep learning came along and this new resurgence of it, it opened up the door for reinforcement learning to be applied to problems where perception was a challenge. So before the latest sort of resurgence of deep learning, it was hard to do problems where the perception itself was vision or language or something like that. That was a big challenge. So since then, of course, we've been doing all kinds of interesting things, like you've seen these things before. For example, here's a reinforcement learning agent we built that learns to play Atari games by observing the screen, so the visual input, and actions being the control of the paddle. This is breakout, and you can see that it actually has learned to do a reasonably good job. Here's another one of a problem from one of my papers with a student, where the agent is in a Minecraft domain. There's a map that is not available to the agent on the right-hand side of the screen. On the left-hand side of the screen, you're seeing the agent's first-person view of the world. It's a very tiny, contrived maze world. The agent's task is to go hit one of the red or blue buttons, depending on if the patterns in the two rooms match. And the patterns don't match, it's a matching and unmatching kind of task. Hit the red or green buttons. And of course, the agent just gets its first-person view and has to learn, and it's not told what the task is. When it pushes the button, it gets a positive. If it pushes the right button, it gets a positive reward. If it pushes the wrong button, it gets a negative reward. Has to learn how to deal with all this. So, perception. Once we have a great tool for perception, we can do interesting reinforcement learning tasks. I've also, as a result of it, become interested in language, but from a very RL-centered point of view, which is that I get to think of language as a solution to the optimal control problem, more directly of setting internal representations of mental states of the listener to solve some multi-agent problem, coordinate to influence whatever the multi-agent problem might be. Right? So that's the view of language that I find interesting from a reinforcement learning point of view of how to use language to influence mental state or influence the internal representation. I'm also quite interested in emergence of language as a solution to a multi-agent problem, and I have a paper back in, I forgot to write the year, maybe 10, 11 years ago, on trying to look at language emergence. But I'm not going to talk about any of that today. I'm going to talk about these two pieces of work. In the 50 minutes remaining or so. The first one is on learning to query, reason, and answer questions in ambiguous text. This is joint work with a bunch of IBM folks, but led by my student, Jean-Jean Gouin, who's now at IBM. And on zero-shot task generalization, where the tasks are defined linguistically. So it's also a piece of work in language, but this isn't about really understanding the language, but instead using language as instruction in order to rapidly generalize to new reinforcement learning tasks. So let's just dive into the first piece of work. So the background of the first piece of work is this little contrived data set called Babby at Facebook, where you're given some context and a question, and you're supposed to answer that question. So the context might be, John is at the playground, Bob is in the office, John picked up the football, the ball thing. By the way, feel free to interrupt at any time and ask questions. Let's make it as interactive as you like. Okay, so this is work from my year 2016. So you give them some context which describes basically the state of the world with people, locations, and objects. So that's the only three kind of things in this particular problem. And again, the question is where is football, and of course we know the answer is background, is playground. And as it turns out, the interesting elements here are there are two supporting facts that are needed in order to answer this question. John is in the playground, John picked up the football, and the fact that Bob is in the office and Bob went to the kitchen happen to be not relevant to answering this answering this question. So this data set came out, interesting deep learning work got done in trying to do sort of question answering in this kind of context. We introduced a variation of this, which we call crack, which I'm amazed that IBM allowed as a name, but it did. For QRAQ, for query, reason, and answer questions, jointly produced by IBM and us. So it's an extension where again we have a context, which let's stay with the idea of people or names anyway, of people names, locations, and objects. So we describe the state of the world in this context, and sort of fully, right? And then there is a temporal sequence of events that occur, also described linguistically. Betty puts down something in the bedroom, Betty picks up the key in the bedroom, somebody goes from hallway to some location, somebody goes from some location to the bedroom. Now we go in and variabilize these somebody, somewhere, some object, V0, V1, V2, V3, and there's still a driving question where it's Frank. And now the intention of going from Babby to crack was to go from question answering to dialogue. So very, very limited, very specific elements of dialogue. The idea is that the system has to now decide what to query the user, the storyteller, if you like. And then, depending on the answers, to ask further questions. This is just one interaction, but we'll see diagrams where it requires more than one interaction. And then finally, once enough information is achieved about the situation, then answer the question. Okay, so is this setting clear? Because the rest of the talk won't make sense if this setting isn't clear. Yes?
I'm sorry, I didn't quite follow. What's the difference between the context and the event?
Right. So it's not a theoretically important distinction. The way to think about it for this talk is that we first define the state of the world, right? Where everybody is, where everything is. And then we define a temporally ordered sequence of events which have some missing information in them, right? And then there's a question and we have to answer the question.
Does the system see the context as well?
All of this is available other than this, which is just showing you the interaction. All of this will be available to the system. All the context events in the question. So the setting is, we're given the context, we'll give the system context, we'll give the system events, we'll ask the system a question. The system has to decide to answer the question or to ask a query. And then when it receives the answer to a query, this process iterates until the system decides to give an answer. And if the answer is either correct or incorrect, and then in the reinforcement learning setting, it'll get a penalty or a reward if the answer is correct or incorrect. Let me just show another diagram. Maybe this will be useful. But let me point out a few things before I go to the next slide. So there are many variables here, right? And the point is, certain variables might be deducible from the context. So Betty puts down something in the bedroom. Well, the only thing Betty was holding was the phone. So it can be inferred, it can be, there's a deduction to be made here that says, I know what B0 is. I don't need to ask, because that's deducible from this. Right? Now, the other things, other variables that might be irrelevant. And you can tell that they're irrelevant. So somebody goes from the hallway to somewhere else, is given the context and the surrounding evidence, surrounding events, makes the value of these variables, V1 and V2, irrelevant to answering the question. Okay, so it doesn't need to ask about V1. And then, of course, the answer to the question depends on variables V3 and V4. Now, by the way, notice that the system chose to ask for V3, but there was another relevant variable V4, could have asked about V4. That would have been a more inefficient way of asking questions. Right? Because V3 either is frank or is not, and you know the answer. V4, depending on the answer, you might have to ask about V3. Okay, so what I want to do, just give me one second here. I want to show this slide, and then if there's still questions, I want to address those questions. Okay, so this is a better view, I think, of what we just talked about. So here's a very stylized context of events. A is in room 1, B is in room 1, C is in room 2, D is in room 3. Somebody goes from room 1 to room 2, somebody goes from room 2 to room 4. Where is A? Really simple. Okay? So now I'm showing you the tree, the policy tree that the system has to figure out to learn what to ask, right? So we divide the variables into deducible variables, relevant variables, and irrelevant variables. And then, whether we know the answer or not. Now the system could ask for B1 or B2 in this context, and if it gets the answer B for variable B1, then B2 becomes irrelevant and the answer is no. If the answer for B1 is A, then B2 is relevant, and the answer is still unknown and has to ask about B2. Let me stare at this tree for a minute and then ask questions. So if you still have a question, go ahead.
Right now?
Yes.
So on the previous slide, the fact basically is I don't know a reasonable answer to give. On the previous thing, it seemed like either that question, whatever it was frank, or it wasn't. And if it wasn't, then he wouldn't know then he wouldn't know where Frank was.
No, he would. Because suppose the answer was who is B3 is not Frank. Suppose it's, I don't know, whoever, right? Then you know where Frank is, because Frank...
Oh, I see, because you had the original context.
That's right.
I forgot. Yeah, that's right.
These events are happening in this context.
Yeah.
Right. Why this might be interesting for a dialogue like... So it's a dialogue in the sense that there are certain paths here that involve asking for multiple things, and what you ask for depends on what the user says, gives us the answer for the previous query, and then eventually you get to an answer and you answer it. So it's a very stylized, very limited kind of interaction, but it is a kind of a dialogue, right? Multi-step, multi-turn interaction with a user.
What are the space of questions that the agent can ask?
Right. Again, the reason why it's limited is because the only thing the system can ask the user is the value of certain variables, and in the end give an answer. So the point is that depending on the path the user's response produces, variables that were relevant before can become irrelevant. Variables that were not deducible before but relevant can become deducible and therefore don't need to be asked. Right? So there's a policy, in reinforcement learning terms, a policy, a mapping from the history of observations so far, right? Observations and action choices so far to what the next action should be, and the action is what variables are. So this is you can think of this as a reinforcement learning problem. Okay, and here's a bigger instance of it. And again, the idea is to show that you can get a tree like this with some very short paths and very long paths and so on. So you can have a depth of this tree, and you can imagine one way to characterize the difficulty of a problem would be the depth of this tree. The worst case depth of this tree. Okay, so how do we solve it? So we do this interaction. Here's a stylized diagram to explain the interaction. Right, the system is given the context and the events, up in the box there. The system is given the question. Literally the events and the context are encoded into the memory buffer of the system. So we're going to use a memory-based neural net. We literally encode, we pre-train the encoding from reconstruction. We take that encoding and put it into the memory buffer. The system, which is basically going to learn a policy, is going to take the contents of memory and the question, and is going to produce an action, and the action it can produce can be, either ask the value of a variable or give an answer. Either it's a query or the answer. And if it's a query, it goes to the user responds to the query by answering the value of a variable. So for example, in the example before, V3 was Frank, and what change that produces is now the sentence encoding changes from V3 goes from V4 to the bedroom to Frank goes from V4 to the bedroom. That changes the content of memory of the agent. And now the memory content has changed. The question remains the same, but the action will differ now because the memory content has changed. And eventually, the memory content might be such that a system can choose to, can know the answer and then should just give the answer. Yes, Jim.
So you're applying this to dialogue. It seems like the same kind of interaction might happen for many other settings.
Absolutely, absolutely.
I mean, I can think of well.
So even non-linguistic settings. So for example, the problem of the matching and unmatching problem I showed you use a memory-based architecture where it would take observation sequences, store things in, decide how to encode them in memory, and solve this problem of either matching or unmatching from what is stored in memory, and then decide whether to go to the left or right buttons, for example. So this idea of taking observations, putting them in memory to build a overloading the word context, but the internal representation of the situation, and then choosing actions based on that, of course, is a pretty general idea.
One thing that seems quite close to the dialogue setting, I guess, is you've got a graphical model, you absorb some variables, you have to pay to query other ones, and you want to query them in some sequence where you can take advantage of their correlations to get an answer to one that might be super expensive to query directly.
That's right. So all of this can be applied. This setting is close to that setting.
So the other setting that came to mind is like a backtracking search solver for a problem like SAT, where you're not exactly querying variables, but you're deciding whether you're going to instantiate them or not in both ways.
Something tells me that somebody has done that, but I can't remember exactly what. But somebody has done something like this for backtracking in a SAT solver. Anybody know?
And Huff do it?
Well, there's Frank Hunter, if that's what you're
I was thinking of Hal and Huff. Didn't they do some...
Somebody, I don't know
yeah.
I don't know who did it. Yeah, so those ideas, yes, the architecture here is a very vanilla one, very generic one, right? The agent has internal memory, working memory. It's going to manipulate its internal memory, write and read in interesting ways to build up, to understand how to interact with the world to achieve the world, right? So the idea of a memory network is not new to us at all, of course. Yeah.
Can the model decide to guess an answer before everything is deducible?
That depends on the reward function, right? If there's a lot of cost to asking a query, it might decide that, hey, it's just guess. And I'll show you some results that may get. It could also, by the way, if the cost of querying is very low, you could just ask all the queries and then answer, because hey, the cost of querying is low, and the risk of getting it wrong, if it tries to be clever, could be too high. So the nice thing about reinforcement, the nice or the bad thing about reinforcement learning setting is that the optimal behavior will be sensitive to the cost of querying. The cost of querying is too high, it may want to guess. The cost of querying is too low, it may just ask everything, it may not want to be clever, all that kind of thing. Right? When you do optimal control, the choice of reward function is important. Okay. All right. I'm not going to explain memory-based neural nets to you. I'm just going to show you how many of you know what memory-based neural nets are? Okay, so not all of you, and that's okay. All I really want to show you is this cartoon diagram in which the sentences are encoded as vectors in memory. The question is encoded as another vector. And then you do this kind of matching nonlinearity kind of process to transform the question and the memory contents into refined questions, if you like, that go through multiple iterations called hops. And at the end of it, you can come up with an internal representation that then is used to compute an answer. Okay, and the whole process is differentiable, and you can differentiate to this based on the error signal. I'll talk about supervised learning and reinforcement learning error signals, and you can train all of this to make it work. That's very, very 50,000 feet view of the memory network story. Okay, so we did it two ways: supervised learning, where we took our data set, training data set, and we made input-output pairs from it. We gave it, for every context and events through the dialogue, the question, exactly what the right answer was, from those trees, if you like, right? We generate a data set where it's supervised learning. So we're telling it for every possible context and events that's experienced in the training data set what the right answer is. That's the supervised learning setting. The reinforcement learning setting, the system has choices of actions. The actions are either variables or answers. So how do we deal with this? We have a vector as output, right? With one unit that corresponds to every variable and one unit that corresponds to every possible answer. So we don't deal in this very simple first experiment with anything out of vocabulary. We just take the entire vocabulary of the entire training and test set and generate a encoding, a output unit for every possible answer and every possible variable, and that's it. Right? All we're going to choose is which unit to light up as the answer. And so in this setting, V2 puts down the key in V3, V1 picks up the key in the bedroom. Who's holding the key? If the system asks for a query, we give it a little penalty because we don't want it to ask too many queries. If it gives the right answer, whether it guesses or not, it gets a +1. If it gives the wrong answer, whether it guesses or not, it's -1. And an example of how we might do it. Right? So in a reinforcement learning problem, we basically have to go all the way to the end to get an answer, and then it'll get a cost per time step in effect until it gives the answer, and it gets a positive. Okay. So we have multiple data. This, by the way, these data sets were generated artificially. We wrote a grammar to generate these data sets, making sure it's working properly and all that. So we know all the exact, the tree, we know the tree and all that kind of fun stuff. So about 100,000 instances per day for training, 5,000 validation, 1,000 testing. We created a data set with basically location of people, location objects, location for alien and sort of aliasing, and locations and with paraphrasing. So we had multiple data sets. At least there are two types of accuracy that we will detect. One is answer accuracy, just basically saying did it get the answer right or wrong. That's more forgiving than trajectory accuracy. Trajectory accuracy is the tightest one, where we basically say did it pick the optimal, did it never ask for an irrelevant variable or a deducible variable, really only ask for things it have to ask for. Right? Now, so getting a trajectory score of 1 would mean that it was perfect. Answer accuracy could be 1 by basically asking all the queries, for example, and giving the right answer. Okay, so trajectory accuracy would be smaller than the answer. So here's first a cartoon sort of result. It's a real result, but just to give you a sense of how things work. So first, let's just look at this figure. This figure, dagger is supervised learning. This is reinforcement learning. That's reinforcement learning with curriculum training. I'll tell you about curriculum training in a minute. But the two bars correspond to answer accuracy and trajectory accuracy. And trajectory accuracy is, of course, lower than the answer accuracy. But this was a very simple one of the many data sets we had, where basically there's only location. So supervised learning is able to do really, really, really well in the answer accuracy sense, and quite well in the trajectory accuracy sense. Reinforcement learning is facing a much harder problem because it doesn't know what the right answer is. It has to learn a policy, so performance falls. And in order to improve the performance, we did curriculum training, in which basically for a little while, we actually positively rewarded it for asking a query, so it learns to ask a query. Before we started punishing it for asking queries, in order to then, after it has learned to ask a lot of queries, to actually reduce the number of queries it asks. Kind of a curriculum training we had to do. And then, of course, then the performance actually goes up. But still, supervised learning is indeed, understandably, as a baseline, better than the reinforcement learning. The point is that in any kind of real dialogue setting, you're not going to have a supervised answer. So if you'll be in a reinforcement learning problem, you wouldn't be in a supervised learning problem in a real dialogue setting. Okay? So now, this is a very busy slide. So let me just break it down. The main thing I want you to think of is the columns of location. The first row is the number of names in the vocabulary, number of variables in the vocabulary. So it gets sort of easier to harder in the location. Let's just focus on location. So this is examples where the only things are locations and people. The thing I want you to focus on is the line that says depth, which is the first, second, third, fourth, fifth line, which is essentially the depth of the trees that has to deal with. So in the 4 to 9 column on the 20 variable thing, it may have to ask for up to 9. It may have to ask for up to 9 things before it can answer, which is a quite detailed, which is quite extensive interaction. Okay, so the reason why I'm having focus on depth is you would expect the problem to get harder with depth, and therefore supervised learning performance to go down, as well as reinforcement learning performance to go down. And within each, I'm giving you answer accuracy for the baseline is just a memory network. The improved one is we had a little trick to improve the memory network, essentially amounting to not using just the last. For those of you who know about how memory networks work, we didn't use just the last hop, but we used a soft integration over all the memory, because the number of hops, here's the logic of it, the number of hops you might need might depend on the depth. And so we didn't want to learn, so we needed adaptive depth. So one way to do adaptive depth is to learn how many hops to use. Another way to do adaptive depth would be to use a large depth to begin with, a large number of hops to begin with, but then learn how to integrate the outputs of each hop. So what we did the latter, that was a little clever thing we did, and that helped improve the baseline to the INP. But you can see, as a gestalt, that reinforcement learning does worse than supervised learning. Some problems are really easy, some problems are harder, and things like that. There's variation in problem complexity here that because we have a generator we can control. So one more result, and I'll go on to the next half of the talk. So this result is focusing on the hardest location data set, so the results are the worst. The y-axis is not performance, the y-axis is a percentage of examples in that data set that had that depth. So remember, the hardest location data set had depth going from 4 to 9. So roughly 30-some% at depth 4, roughly 40% at depth 5, and so on. And so the height of the bar is the percentage of problems with that depth. The shading in the bar is the supervised learning performance with these diagonal lines, and these dotted shading is the reinforcement learning. The first thing, of course, is when you go from supervised learning to reinforcement learning, the performance drops quite a bit. The drop should get larger with depth, so that's not really quite true. Because, for example, supervised learning seems to be doing quite well here. And this is what the empirical results were. This is with answer accuracy. This is with, and the last one is with trajectory accuracy. So the other thing that should happen is the trajectory accuracy performance should be smaller. I think it is with respect to the answer accuracy. Okay, so that's it. I'm going to just say that about this piece of work. We have a context, we have a sequence of events and missing information. The agent has to interact with the user to learn the missing information. We want to ask only for missing information that's relevant, that's needed in order to answer the question. This kind of simple memory network architecture is able to deal with, the problem at least after a fashion. So just a very quick summary slide. I'm actually working on conversational systems quite a bit these days. We're trying to build a real conversational system to actually use the undergraduates to advise their undergraduate curriculum on curriculum choices. It's an open-ended, hard problem, how to build conversational systems. But I think there's a lot of exciting stuff going on right now. There's new data sets, including ongoing collections. Sad part is most of that's happening in industry. Hopefully industry will share, and we will get to work on them in a few days. This is also really exciting. A lot of interesting integration of dialog system work with databases and knowledge graphs and access to external sources of information of various sorts. It's being integrated really nicely. And that, I think, is also very exciting for the dialog system. So I'm excited to be working in dialog systems after a paper 15 years ago at AT&T. It's an exciting time. So any questions about dialog systems? I'm about to move on to this other task, which is instruction taking using linguistic description of tasks. Yes.
So I think maybe I misunderstood. So in the supervised setting, are you saying that you actually knew what the best answer, the best question to ask was, or the best?
Yes.
Okay.
We literally gave it every step what it should do.
Okay, and so then the reinforcement learning, did you use, basically what reinforcement learning algorithm did you use? Did you use LOLs to mirror Dagger?
No, we just did policy gradients. We give it a penalty for every query question it asks, and when it chooses to give an answer, we reward it or punish it depending on the answer. Are there better reinforcement learning algorithms? Probably, but I don't know how much of a difference it makes. We could probably squeeze out a few more percent if we were clever about it.
I think this does raise the question of how well planning might do. So when you're planning, you have to integrate over the unknown answer.
Right.
But there is still a best sequence of questions that you could ask. If you had an oracle to tell you the answer and you tested that as an upper band, but there's another one which is the best sequence of questions you could ask if you don't know the answer, which is still well defined.
Right. Right. There are many possible worlds for any given context and event, and there will be a sequence of answers. But remember, the sequence of answers should not be open loop. Sequence of queries should not be open loop. It should be closed loop. That is, there's a tree,
Yep.
which is the optimal tree.
Yep.
And those are the trees that I was showing you. I was showing you optimal trees. Well, I was showing you optimal trees for a particular instance. You're pointing out that there's an optimal tree
For every instance.
for the worst case sort of instance.
Yeah.
There's an optimal tree. There's a tree for the worst case instance, and that's what we could compare against that. We did not. Yeah.
Is it possible to characterize the difficulty of the problem in terms of the variables? So, for example, when you increase a variable, does the length grow linearly or exponentially, or if you increase the types?
No,
of
so we
parameters?
did measure it precisely. There are many ways of possibly measuring difficulty, right? The number of names in the vocabulary, the number of names in maximum number of names in an instance, maximum number of variables in an instance. But really, and all those will add to some level of difficulty. But we found the depth was, we surmised the depth is an interesting one, which is the depth of the tree for that instance, right? The worst case depth.
So do you know, does it grow linearly, exponentially, or it really depends?
Does what grow linearly? The performance decrease linearly, exponentially with respect to depth? I don't know if you can tell. Depth should make the problem harder, you would think. But I don't know if I can assert anything on linear.
I'm just wondering, when you said you're going towards larger conversational systems,
Right.
involving the undergraduate curriculum, right? That blows up the number of variables, the number of types of questions, and I'm just wondering, how much leap do you have to cover when you go from this problem to that problem?
Okay, so the reason why conversational systems are hard is not because of this issue per se, it's because of flexibility of language and the larger context. So I don't know, when you go to, I actually am doing advising this year, and an undergrad comes in, and I ask them how they're doing, and the conversation can go off in so many different directions. That's the challenge. I don't know reasoning like this. I think reasoning is a component, right? For example, reasoning might be, I'm taking this class, is this going to advance me towards my degree, or if I take this path? Those are reasoning-like problems. And there's some incomplete knowledge and incomplete observations. So this is a very particular aspect of the conversational system. The general difficulty of the conversational system is, of course, what is the goal in the first place? And what is the, and of course, conversation goes off in so many different directions. How do you handle all that? Just understanding what they're really asking. They might be asking, is this class, should I take this class? But they might be asking, is the instructor really any good? Is the instructor too hard? Who knows what they're asking? So there's all kinds of linguistic subtleties. So yes, this was a very particular, focus on a very particular slice of that conversation system. Yes?
So the toy task that you were just dealing with had deterministic reasoning, but if I understand correctly, the method would work just as well if it were probabilistic reasoning, right?
Agreed. Yes. Agreed. And we did use very similar architectures, for example. A memory-based neural nets for reinforcement learning are used stochastic domains. Okay, I'm going to now switch to another language-inspired task, but less linguistic, to coin a term. Zero-shot task generalization. This is work by Junyu Go and colleague Hong-Lak Lee and a colleague. Well, at that point, it's Microsoft Research, but now at DeepRL. Everyone is going to do it. So the motivation for this work is, so the high-level motivations work was to really go towards rapid generalization in reinforcement learning. There are many ways to approach the rapid generalization problem. The one that this book focuses on is to imagine that the one way we get rapid generalization is that task is described in some language, described in some way. And there are many ways you can imagine describing a task. So the way we're going to look at describing a task is through language, very simplified, simple language. So for example, pick up a pen, throw a ball, and what you want the system to learn is to generalize rapidly, having learned how to do these tasks. Throw a pen. So there are nouns and there are verbs, right? Noun, verb. And literally what we're going to do is we're going to train the system on every noun, on every verb, but not on the entire cross-product space. And we're going to try to generalize to unseen noun-verb combinations. Okay? That's the first kind of rapid zero-shot generalization we want to do. The other we want to do is that, let me just go. So this is the one I just told you about, going from training on all nouns and all verbs, but going to unseen combinations. The other one is looking at sequences of instructions, of tasks. So go to A, go to B, go to A, something like that. And then going to unseen lists, unseen sequences, but with seen instructions. And then, of course, going to very long lists with unseen instructions in the middle. Okay, so that's what we're about to do. So let me now ground this task in a video of it working. Let me just say a few things, first of all. So we just give these symbols, right? No semantics, no language, no linguistic understanding. We just give them as encodings in memory, right? And the system has to act in the world. And you'll see it acting in the world in a minute. And the only reward it gets, we're not supervised learning, we're doing reinforcement learning. So the only feedback it gets, it has a cost per time step because you want to do it quickly. And then if it succeeds at the end, it gets a pat on the back. If it fails, it gets a kick. That's it, right? So it's a very delayed consequence kind of thing. So we're learning to understand these instructions and generalize unseen instructions from delayed feedback while acting in the world. Okay, that's the setup. So let me just show you this video to ground it more. So this is again a Minecraft-like domain. On one side you see what the agent actually sees. This is a map of the world which is not visible to the agent. That's the list of instructions. Okay, so and I'll show you the video again at the end as a result. I just want to show you some. So there's the agent. It's acting in the world. It's moving in the world. It's seeing this kind of partially, first-person view. It has to transform 3 cats. It has to find a cat by looking around. Found a cat. It transformed it. It's now visiting a horse. Then I just jump forward. So now, anyway, and now here's the one I'm going to show you quickly. Then I'm going to walk you through how he did it, and then show you this result again. So you can see a very long list, right? And the system has to figure out what instruction should it do, and when is it done with that instruction, so we move on to the next instruction. And it only gets a reward at the very end if it has done this entire thing properly, which is 1,000 steps of actions maybe, or whatever, hundreds of these.
So I'm confused. It seems to be going in strict order.
Yes, I am creating this, I should have said, this sequence. I wanted to do it in perfect sequence.
So, but you said a moment ago, I thought that it should decide when it gets to the end of an action, whether it should go on to the next action.
When it,
or which action.
when it has success, it has to learn when it has succeeded at finishing an instruction in order to know to go on to the next one.
Got it.
Because nobody tells it, right? It's just acting in the world.
Rewards only at the end.
Rewards only at the end, right? Okay, so now let's go to the next. So now, what are the challenges? I'm going to walk you through now what we did, and then I show you this video again so you have a better understanding of this. So, first of all, just solving unseen subtasks itself is a hard problem, right? Generalizing to new noun verb pairs is itself a hard problem. Deciding when to move on to the next instruction. Agent is not told which instruction to execute when. It should detect when the current instruction is finished. It should keep track of which instruction is solved. And furthermore, what I did, if I were to tell you, is that each instruction is a noun, count, and word. So it might say pick up 2 cats, or pick up 2 eggs, or whatever, right? So then it has to have an internal counter that says, oh, I've only picked up 1. Now I need to pick up a second one, or pick up a third one, and so on. Right? It has to do with that. Furthermore, there are some random events that can happen. Like randomly a treasure box appears that's not in the list of instructions. It has to interrupt whatever it is doing, go pick up that treasure box to get the reward, and then go back to that instruction and finish it. So random events can occur, and to learn to interrupt whatever it's doing when the visual observation shows the random event. Random opportunity for reward, picks it up, accumulates that reward, then goes back to deal with that. And then, of course, it has to deal with, in principle, unbounded number of instructions. Okay? And, of course, all of this with delayed reward. Okay, so here's our architecture in a boxology sort of view. We're going to build a hierarchical reinforcement level controller. We're going to build a multitask controller with the lower level, which is going to take subtask arguments, essentially nouns and verbs. Right? It's going to act in the world. It's going to learn when it thinks it has done with that, with whatever it's being told to do by the higher upper level meta controller. It has to learn when it thinks it has terminated. It passes that signal to the meta controller, which also gets the real observation, the first person view, right? Both the meta controller and the multitask controller get this first person view, and the meta controller is given the list of instructions in memory. This is the architecture, right? At every point of time, this is a discrete time task. Every time the meta controller has to decide what is the task that the lower level controller should be doing. Encode the instruction to subtask argument appropriately. The multitask control job is, given whatever I'm being fed by the upper level, what should I do, and am I done? And then the meta controller has to, keep track of what is being done, where it is, what it should do, and when to move on. Okay, all right. Let's show you the details of the subcode arguments. No, let me show you. Let me show you this diagram. Okay. So this diagram is, and I apologize for those of you who are not familiar with deep learning architectures. I'm going to be fairly quick about it. But essentially, the subtask controller gets the observation, or actually maybe a history of observation, which is the first person views, images, as input, and is going to map those to physical actions and simultaneously whether it thinks it has terminated or not. It has accomplished this task. Which task? This task. These are arguments, noun and verb pairs, that are given by the multitask control. These are the subtask arguments, by the meta control. And we do what's called parameter prediction in deep learning. Basically all it means is that the weights that go from input to output are a function of these inputs. So in other words, when I change the task, the mapping from input to output changes, and the function of that, and I'm going to learn all these weights in these in these edges. And I do convolutions, of course, because, of course, we're doing visual processing, so convolutions makes sense. Okay, so I'm going to tell you about, there are many things I could tell you. The thing I'm going to focus on is one trick that was pivotal, which was the idea of analogy-making regularization. So the idea of analogy-making regularization is, remember, a meta-level controller has to decide what two arguments, two vector arguments to give. Think in your head, noun and verb. So this is a lovely idea that's not new to us, but we use that as we added this objective to this task, which is that whatever the representation of pickup A and visit A is, the difference between those two vectors should be close to the difference between pickup B and visit B. Because if I subtract these two, A is common and I get the difference between pickup and visit. And if I subtract these two, B is common and so I get the difference between pickup and visit. And you can also do this with the orange arrows. So we impose that as an additional objective constraint to the overall problem of here. The overall problem for the learning the multitask controller, right? I mean, we do some policy distillation. In the end, I don't think it mattered a lot. If you know what policy distillation is, we did use that trick as well. But really, the final objective was the RL objective. Did you complete the task or not? Plus the analogy making objective. And during training, we're also learning the termination. So whether it's correctly terminating or not. All right. So before I dive to the meta-task controller, I should be very clear about this. We first separately train the multitask controller on single instructions, on a subset of noun-verb combinations, showing it all nouns, showing it all verbs, but not showing it cross-form. We separately first train that. So now it's trained. We evaluate how well it generalizes. It generalizes really well to unseen noun-verb pairs, so we're confident about the multitask controller. Then we move on to train the meta controller. Meta controller has the following problem. It also gets the observations or history of observations as input, last k observations input. It's going to map that to, in the end, to the subtask arguments for the multitask controller. That's an end. That's that mapping. It's going to let that mapping be influenced, be a function of multiple inputs. One is, what is the current subgoal? Which, by the way, I should say, before I come back here, I should say, it's maintaining a pointer into memory. That pointer into memory is essentially telling it which subtask it thinks it's doing. It should be doing. And that memory pointer can be incremented or decremented. So we never end up decrementing because we always want to keep moving forward. So what current instruction is following, and what did it give us output the last time, whether the multitask controller thinks it's terminated or not, and then there's an entire differentiable process over all these different elements of the network in order to train the multitask meta controller. Yes, Jason.
So I just want to point out a connection for people in the audience that this is a lot like attention in machine translation, where there's some input, in this case a sequence of tasks, and some output, a sequence of actions. And there's some work by Trevor Cohen et al. On making sure that your attention proceeds monotonically through the sentence,
yes,
through the input sentence.
Yes. This is going to do monotonic. Even though, again, we allow it to backtrack by one, in the end, that's not what we wanted to do, so it learns to not do that. It just keeps going forward. By the way, the other thing is, when the instruction is pick up 2 eggs, it doesn't tell the subtask controller to pick up 2 eggs. It just tells the subtask controller to pick up an egg. Because the subtask controller is never trained with counts. The meta controller has to learn, even when the subtask controller says it's finished picking up an egg, it should say, I'm not done yet. I need to pick up 2 eggs. It has to have an interval. So there's an LSTM we did it both ways. But there should have been an LSTM, there should have been a recurrent connection in this diagram, which sort of keeps track of how the exit thing gets picked up. We tried multiple architectures there, and I'm going to misremember which one ended up being the best. But we tried LSTM, and we tried other ways to deal with memory with the memory. Okay. Okay, I'm nearly out of time. So what I'm going to do is I'm going to just show you the results again, or the visual again, and then we can answer questions. Okay. So this is initially with random latent display, nothing terribly interesting. Again, this is what it observes. That's not visible as for us to consume. What it thinks, what the agent should execute is in this. What the agent is reading is the blue. It is performing is written up on top. Okay. This is random agent, so it's not terribly interesting. The index is moving around arbitrarily. After it has been trained on training instructions, you'll see it do sensible things. So picking up two pigs, pick up pig. Now we pick up one, transform 3 cats, transform them, return to ice. The random magic box appears on top. Even though it's not in this thing, it has to now subtask transform box. It tells the lower level agent to do that. Then it goes back to transforming 3 cats. I think it already done 1 or 2, I can't remember. First of all, I have to find the cats, right? I found the cat, now I'm going to visit a horse. I'm going to visit a sheep, and then done. Now look at longer instructions. It's actually amazing that this works, but it does. By the way, those were not slowed down. It's actually faster than even this. This is still slow. Those are not sped up. This is not sped up. It's actually faster than this. But it would be a blur if we showed it faster. And here, it's doing the counts. It's doing. Hard to verify this is the right thing. But what's really one of the impressive things here is that it has findings. You can't see them because it's got a visual, tunnel.
So is there evidence that it remembers where things were, and is there evidence that it's doing planning?
Just as I was saying that, I'm thinking in my head, somebody's going to ask me that question, and what am I going to say? We didn't explore that. That's short. But just as I was saying, I'm thinking, that's a natural question to ask. Here's a good one. Okay, so you can watch in the background but ask questions. Go ahead.
Just a question. What happens if you give it a task that, have you tried giving it a task which it can't complete? Like visit horse and there's no horse?
Yeah.
What happens?
Yeah, we did that.
What happens?
So I think it just keeps trying to look for a horse.
It doesn't move on.
It doesn't move on because eventually it will, right? Because the memory pointer stuff will eventually, because there's some stochasticity in there as well. Eventually it'll just jump. So yes. And then it'll try to do the next instruction. But it's not a learned behavior. That, hey, I can't see a horse. I should move on. Because the interpretation we're giving it, you only get a reward if you execute these instructions exactly in sequence. Okay, I'm basically done. I have a concluding slide, but if you have, just let's ask questions if you have. Otherwise, I will show you another slide. Okay, so there's lots of ways to do this. We just did a hierarchical reinforcement learning approach to this, unlimited number of instructions. What I'm really interested in is enriching the set of instructions to make loops, to do more general program execution, where the program involves the agent behaving in the world in this way, right? Where each instruction involves learning a policy and the stochastic, dealing with the stochastics of the world as well. A more general, in lots of ways, right? It doesn't have to be sequences list. It could be a set of tasks, and to learn how to do them optimally, in what sequence to do them. There might be the usual old AI stuff like goal covering, and to learn how to do this kind of thing properly. So you can make this richer and richer. and we're gonna try to go down some of those steps. And to be fair, the line of work that most deeply connects to this is a neural program, neural instruction executor, or something like that. All the neural program stuff, right? Except they are not doing it in an RL setting. We're doing it in the RL setting. And how big a difference that is, we can talk about that. Look like you have a question. Go for it.
So it seems like your planning module is also neural, right? And your perception and your feature extraction.
So I'm not planning. In the RL world, we reserve the word planning. We're using a model to simulate the world. I'm not planning, I'm doing policy learning, right?
Right. Sorry. So your model of the table, like I guess what I wanted to ask was if you had a finite machine, because you sort of have a closed world assumption, you know what words are, how many counts there are, what nouns are. I guess it would simplify the action of the policy space of the agent and just use the neural networks for doing the feature extraction, for getting the features. Like, have I jumped to the next stage?
Yeah, you could use neural nets just for feature extraction to feed into a different finite state controller. Sure, you could do that, but you would have to use the knowledge to build a finite state controller. And yes, there are many ways to do it. Yeah, this is surely not the only way to solve this problem. And of course, we don't really care about this problem, right? We care about the problem of how do you take natural language instruction and learn to generalize to unseen, unheard natural language instruction. That's the goal here. And to take richer natural language in the end.
I have a clarification. When you train the meta controller, you only trained it on the specific pairs of actions and objects.
The lower level controller, multitask controller, was trained first, pre-trained, if you like, on noun-verb combinations. Some subset of the a small subset of the overall noun-verb combination pairs.
So is there? So I was assuming that at some point when you say generalization, maybe there's some
Yes.
notion of some nouns and verbs don't go together, but in this
in this setting,
example,
all
they
nouns and verbs go together. If they didn't, and you have to learn that, it would be interesting. We did not. We did literally have a space in which cross-product space was viable. And the paper has generalization results. We show you, how well it generalizes. I'm not showing you all the details. The paper has it, yes.
So it seems like, or did you do any experiments where you trained the whole thing together instead of first training the nouns and verbs? Because it seems like the system's only, like you're building these pretty good executions of a noun-verb pair, and then you're just choosing between them, and like if you didn't have this distinction, it seems like you'd probably just like walk around a very, very high-dimensional parameter space and not find anything.
Definitely helped to pre-train the subtask controller, the multitask controller. Definitely helped. We tried all kinds of baselines, and they are reported in the paper. A non-hierarchical baseline does miserably, because tasks are really hard, right? This is a really long sequence, so it fails quite badly. So hierarchy helped, analogy making helped. Remember that the meta controller has to learn to translate an instruction to arguments that allow for generalization. That's actually a pretty interesting task, interesting challenge in and of itself. Because generalization is to policy parameters. In policy parameters space. So is your question, would it just still work just as well if you just hadn't done this separate training? The answer is we didn't have that experience. We tried. Did not have that experience. It really helped to train this stuff. It's not that it wouldn't do anything interesting if we trained it together. It did, but just wouldn't work nearly as well.
Yeah, well, I guess my question is more like, it seems like you took this noun-verb combination and you made it to a task, which seems like something that's been done in other papers, I imagine, and then you took something that just chose between.
No, because remember,
different
there's lots of challenges to the meta task, meta controller. First of all, it doesn't really know when a task is finished. It can learn to ignore the termination because the termination can be noisy. It has to be able to interrupt the current instruction and deal with the stochastic event, and then go back to it. It has to learn to count because the instruction might be pick up 5 eggs, and it has to learn over this temporally extended sequence without supervised learning whether, how many eggs have been picked up. And so even if you give it a perfectly trained multitask controller, the meta controller's task is still quite a challenging task because it has to learn to generalize, it has to learn to give the right, it has to learn how to activate the subtask controller correctly, right? It has to deal with termination, it has to do stochastic interruptions, things of that sort. But yeah, that's a good question, which is to say, that is the decomposition we are working towards, right? Where the lower level learns how to execute these instructions, the upper level learns what instructions to give. That is true. Yes.
So, follow on how long does it take to train?
In the Minecraft setting, I think we did multiple. We did a little 2D visual domain as well, 2D grid world as well. It takes a couple of days to train. And you can make the task harder, take a week to train. Make it harder to take longer. But these days we're not scared by a couple of days of training.
Good.
Very much.
Okay, well, thanks to Satinder for a great talk.